When we did least squares regression, we defined the total error of the model by the sum of the squares of the residuals. It's not really the error of the model, but it was our measure of how far our model was from being the best we could come up with. Why did we define it by the sum of the squared residuals? Well, let's suppose that the data actually do equal our model. It's a straight line, plus zero mean IID Gaussian white noise. Now the model we used was white noise. Now we're assuming zero mean IID independent identically distributed Gaussian white noise. Then if the model is correct, the residuals are zero mean Gaussian IID noise. So the probability density function for any single residual is the normal distribution. Since the noise values are independent, the joint probability density function for all of them taken together is the product of their individual probability densities. Now, it's often useful to use the log likelihood function, which is just the logarithm of the joint probability density. Here I've called it by the uppercase Greek letter lambda, and it's the logarithm of what we call the likelihood function as a function of the residuals, which is this expression here. To choose our model, we chose the parameters which gave the greatest likelihood of the observed data. But which one is it? Well, maximizing the likelihood function is equivalent to maximizing the logarithm of the likelihood function. Maximizing the log likelihood is equivalent to minimizing the negative of the log likelihood. So what we really want is to minimize this quantity, negative log likelihood, which is this quantity here. Notice that it contains terms involving the variance, it contains constants like the number of data points and 2 pi, but it also contains only one term involving the residuals, and that's this sum of the squares of the residuals. It turns out that the regression parameters which minimize the log likelihood are those which minimize the sum of the first term only, that is, which minimize the sum of the squares of the residuals. But this is just the sum of the squared residuals. Therefore, when the data follow our model plus zero mean IID Gaussian noise, least squares gives the maximum likelihood solution. And that's why it's so good, one of the reasons, and it's also one of the reasons it's so popular. Now, least squares is the maximum likelihood solution when the noise is zero mean IID Gaussian. Since that's the most common assumption about noise in time series, the least squares solution applies in a large number of cases, but its applicability is even wider because of a result known as the Gauss-Markov theorem. It tells us that for white noise, it doesn't have to be IID, it doesn't have to be Gaussian. For white noise, the least squares solution is BLUE, and BLUE is an acronym standing for Best Linear Unbiased Estimator. Best means least variance, that is to say, the uncertainty in our estimated parameters is as small as possible. Linear means that the solution is a linear function of the input data. Unbiased means that the expected value of our parameters that we estimate is equal to their true values. In a wide variety of cases, we shouldn't expect to do better than least squares regression because it really is, according to the Gauss-Markov theorem, the best linear unbiased estimator. That's what makes least squares regression so good, and a big part of what makes it the workhorse of regression modeling, and with good reason.